Hi there, welcome back. Well, I haven't changed a thing as you see here. Oh wait, I have changed something. We were talking about the ideal gas law and I was sort of motivating things using this plastic bottle. The problem, of course, was that my plastic bottle was filled with water, and water is certainly not a gas and doesn't obey this equation. And so I've solved that problem. I drank the water. So now I have a container of air, okay, gas particles, okay, and so I'm going to make a couple assumptions. To start off with, I'm going to assume that that the air here is actually going to behave like an ideal gas, which is a pretty good approximation as it turns out. I'm also going to, I don't know if you can tell from there, but there's little droplets of water on there. I'm going to ignore those, okay, and so we'll just, as a small complication. So I have emptied out the water and replaced it simply with air. Now, I should point out the stuff that I was saying in the previous recording about the particles bouncing around, colliding with the interior surface of the bottle, and therefore exerting a force, therefore exerting a pressure, holds true for water just as it does for air, but the mathematical relationships between the pressure, the volume, and the temperature are more complicated for liquids than they are for gases. And we're doing gases right now, so we'll stick with that. So, oh, but by the way, now the gas molecules are going to fill up the entire volume here. Okay. This small bit up here is a small correction to the total volume. And in fact, actually, when I look at it, I look at the volume of this thing. I could read it off here. I said 500 milliliters. All right, and so that includes this top bit. And so what I'm going to make a small approximation if I ever need to. If I ever need to care about the area, I'm going to model this as approximately a cylinder, and so that I know what the surface area of the cylinder is. It's 2 pi r, the radius of the cylinder, times h, the height of the cylinder. So if I ever really want to calculate it, I could. But anyway, there's our object there. Okay, and let's just start out. Let's do an example. The thing. Let's see what we know. Well, we know the volume of it. I can read the volume off the label there. I know the temperature. I can feel the temperature in the room, and the temperature in the room right now is about 20 degrees Celsius, which is 293.15 Kelvin. Because I'm only estimating the temperature in here, but we'll just round that to 293 Kelvin. And I know the pressure. Because I said here a moment ago that 1 atmosphere of pressure is the pressure that the atmosphere exerts on you and on everything, including, for example, this bottle. Okay? So in other words, the pressure that the air around this bottle is exerting is 1 atmosphere, which is this many pascals of pressure. Okay? And I can tell you, therefore, that the pressure inside the bottle is also 101.3 times 10 to the third Pascal. I know it has to be because this bottle is not crumpling into a little plastic ball, okay, or it's not exploding either. So the pressure inside has to be equal to the pressure outside. Since I know what the pressure outside is because it's caused by the atmosphere, the pressure inside has to be equal to that. So I've got the pressure. So I know the volume, I know the pressure, I know the temperature. R is a constant. Hey, this way I can solve for the number of moles of gas inside here, which, to be honest with you, off the top of my head, I have no idea. So let's calculate it. No, stay here, I guess. Okay, let's see. So the question is, how many moles of air do we have inside there? Fantastic. Okay. We're going to have to do one thing that we're going to have to be a little bit careful of, but it won't be difficult. All right, let's see. PV is equal to nRT. I should start with a drawing, but I guess I've already got one here, right? And I could label this, I suppose. So I could say, okay, well, there's the volume, and the temperature is the ambient temperature around here. The pressure is the force per unit area, but we've already talked about this. So we already know what that number is, so I'm not going to worry about that. And the number of moles of those little blue dots I've got there are as a constant. So we want n. We'll solve for n. So n is equal to PV divided by PV over RT. Okay. And let's see. The pressure is, so we just plug in numbers, 101.3 times 10 to the third pascals. That's the pressure. The volume is, whoops, okay, we better be careful here. The volume is not 500 milliliters, or I can't write it as 500 milliliters because I need to work in consistent units in the SI system. Liters is not part of the SI system. So how many cubic meters in 500 milliliters? Let's find out. Hey Siri. How many cubic meters in 500 milliliters?
0.0005 cubic meters.
Okay. Thank you.
You're most certainly welcome.
Of course, by doing that, I just erased my number. What was it again? Repeat the last calculation.
You're most certainly welcome.
Sorry about this. How many cubic meters in 500 milliliters?
That would be 0.0005 cubic meters.
0005 cubic meters. Okay. And then R is 8.31 joules per mole per Kelvin. And then our temperature, we decided, was 293 Kelvin. Okay. And I'll punch this up. In fact, I'll tell you what, I'll pause the recording. Punch it up while I'm going. Okay, and if I have it, if I punch it in correctly, I'll get 0.021 mole. All right, let's do a quick sanity check on our units. Let's see. A Pascal is a Newton per square meter, and so we have Newton over square meter multiplied by cubic meters. So our meters squared divide out, and 2 of our 3 meters divide out there. On the bottom, we have joules over mole per Kelvin. So we have Kelvin in the denominator here, Kelvin in the numerator there, so those divide out. A joule is a Newton times a meter. This is Newton times a meter, so the joules divide out with the Newton times meter. And so we're left with 1 over moles. Yeah, sure enough, we end up with moles. And as far as the number is concerned, this is about 10 to the third. This is 1, 2, 3, 4. So that's 10 to the minus 4. So this is 10 to the minus 1. This is 100 times 10 to the minus 1 is about 10. 10 divided by 8 is roughly 1. 1 over 300 is about 0.003. This is 0.02, so we're in pretty good shape. Okay, so 0.02 moles roughly of air inside that container. So that's the kind of calculation you can do with the ideal gas law. Okay. All right. That was exciting. And now you know something. This is about 2/100ths of a mole worth of air. Having done that, now there's another thing we can think about. If I take my little bottle of air, suppose I am not content to simply look at it and admire it, but I actually want to do something with it or to it, specifically change one of those variables in PV equals nRT. Well, let's say N is the number of moles, so I could add more gas. That would increase the number of moles. That seems like I'd have more particles colliding with the surface, so that might increase the pressure. I could artificially increase the pressure, right? And so if I increase the external pressure, at some point, I can't crush the bottle anymore, not without destroying it, which I don't want to do. And so what happens is the reason I can't crush it anymore is because the internal pressure has now balanced the additional external pressure that I'm creating by squeezing, okay? So I increased the internal pressure because it responded to my method of doing that, which was to increase the external pressure. So when I increase the external pressure, the internal pressure automatically increases to compensate until it reaches equilibrium, at which point the internal pressure is now increased. Okay, so I can do that. And in this case, it's not obvious, but as it turns out, it looks like I might have changed the volume of this thing, but in fact I didn't. I changed the shape of the container, but I didn't change the volume of the thing. So you can think about that and convince yourself of that. In any case, so that's that. So I can change the pressure, I can change the temperature, right? I could hold it in my hands and let it warm up. But if I do that, then I'm adding energy, right? Heat is flowing into the bottle here, right? But heat flows in, that gives the particles more kinetic energy per particle, which of course that's what increasing the temperature means. But again, now that the particles are moving faster, they're colliding with the surface of the container more vigorously and increasing the pressure therefore. So increasing the temperature is another way to increase the internal pressure. I can increase the internal pressure by increasing the external pressure. I can increase the internal pressure by adding more gas. That's what happens. That's what you do when you when you inflate a balloon, right? You add more gas, add more moles. Or I can increase the temperature. And of course, you can do more than one of those things. You could do several of them. You do all of them at the same time. So, or you could decrease the pressure by releasing some of the gas or by lowering the temperature, okay? Or by somehow expanding the volume of the thing, if you could figure out a way to do that. So there's a lot of relationships, but here's the thing. Based on everything that I was just saying, so let's think about the pressure, the volume, and the number of moles. Those are the things that you can change. The pressure, the volume, the number of moles, and the temperature, sorry. Okay? You can change P, you can change V, you can change how much gas is in the thing, and you can change the temperature. Okay? Now, let's suppose for a moment, let's leave changing N out of the equation. Why? We want to have a closed system, not an isolated system. So we're still going to allow energy to flow back and forth through the boundaries of the container. But let's suppose that we don't allow any mass or matter to move into or out of the system. So that's the definition of a closed system. Matter can't change, but the energy can. Okay? In which case, so these things are changeable, but for my present conversation, let's let N be constant for our given experiment. Okay, some other experiment we might not do that, and we wouldn't have to, but let's assume that we do here. Okay. Well, if so, then furthermore, let's assume I want to be able to change any or all of the other quantities listed there. Well, if so, then let's do this. If I'm going to change them, then that means that my pressure, my volume, my temperature are going to have some initial values, some starting values, a first value. And then after I finish doing whatever it is I'm doing to the pressure, to the volume, to the temperature, all three of those things will have their final value, their later value, their second value. Well, before I start fiddling around, the relationship is P1V1 is equal to N times R. Remember, we're assuming that N is going to be constant, times T1. Right? And after I have finished doing whatever it is I'm going to do, this relationship also holds. Remember, R, of course, is a constant. And now I'm going to be clever. And I'm going to divide this top equation both sides by T1. So P1 over V1, P1 is equal to N times R. Same thing for the second equation. P2 times V2, T2 is equal to NR. Okay. Aha! Here's the thing. I now have this left-hand side, so this quantity here is equal to NR. This quantity here is also equal to NR. Remember, N is a constant only because we're assuming that it is. But since these two things are both equal to NR, they must be equal to each other. So that gives us V1 over T1 is equal to P2 V2 over T2. And this is a useful relationship as well. It is semi-independent of the ideal gas law. It's derived directly from it, except it has an additional assumption built into it, which is, again, that N remains constant. You don't change the amount of gas that's in your particle. You have a closed system. So with that assumption, which is a very common situation, then you have this relationship, and this makes it nice and easy. But what this tells you, I mean, there's a lot of easy calculations to do here, but the physics behind this particular expression is that changing any one of these physical quantities automatically alters the others. Okay, and I described that a few minutes ago. So this is a nice, useful relationship, makes for easy, as I say, easy calculations. But the thing I want you to pay very close attention to and really get is the physics that this relationship expresses. Okay, so that's good. Next thing I want to talk about, next recording, is, okay, so yeah, I can change the pressure, and as a consequence, the volume and temperature will change. Or I could change the volume and the temperature and the pressure will change. Or I can change the temperature and P and V will both change. Does it matter which one I do? Does it change anything? You know, is there any difference in the behavior of the gas and the behavior of the system if I change the pressure versus changing the temperature versus changing the volume? Do they all have the same effect? How does that all work? That'll be the subject of the next recording. I'll give you 3 guesses.